In the previous lecture, we started a discussion about the forces acting on aircraft during flight. For that purpose, we took a very simple situation, a horizontal flight at constant speed. In this case, there are four forces: the weight, the lift, drag, and thrust. The equilibrium equations are also very simple. Lift equals weight and drag equals thrust. In this lecture, we will focus on the lift force. The lift force is given by a rather simple equation. The lift is equal to a constant CL times the product half rho v squared times S. The meaning of these parameters are as follows. CL is the so-called lift coefficient. This parameter will be discussed in more detail on the next slides. The rho stands for the air density, the V for the airspeed, and S is the parameter for the wing area, which is the surface area projected on the XY plane when we take a Cartesian coordinate system and where Z is the vertical direction. For all parameters except for the coefficient, the dimensions of the parameters are given. The question is therefore, what is the dimension of CL? How do we determine its dimension? In this case, we use a dimension analysis. Such analysis can also be used to check whether a formula or equation is correct. If not, the dimensions on both sides of the equal sign are different. In our case, we can fill in the known dimensions of the parameters. First, we use a question mark for the lift coefficient. On the left-hand side, we see newtons, and on the right-hand side, we see kilos per cubic meter times meters per second squared times meters squared. First, we replace newtons by kilos times meters per second squared. Next, we eliminate as much as possible on the right-hand side. It happens to be that in the end, the lift coefficient has no dimension. The lift coefficient, which is dimensionless, includes a number of aspects of a particular wing, like the geometry, the airflow around the wing, etc. Key parameters influencing the lift coefficient are the angle of attack and the geometry of the airfoil, which is the cross-section of the wing in flying direction. The airfoil is usually not symmetric. If we draw a straight line between the front, the leading edge, and the rear, the trailing edge, it becomes visible that the profile has a camber. A camber means that the line precisely in the middle between the upper and lower surface has a curve with respect to the straight line. That straight line itself is a chord line and may have an angle with respect to the airflow at some distance in front of the airfoil. This angle is the so-called angle of attack and has a significant influence on the lift. Because of the importance of the airfoil, a lot of experimentation has been done in the early ages of aviation, searching for the ultimate airfoil. This resulted in a wide variety of airfoils, as can be seen on this slide. What is remarkable is the fact that many airfoils have their own code. Later, in the 1920s, a more systematic nomenclature was introduced, which is still used today, the NACA profiles. NACA stands for National Advisory Committee for Aeronautics, a committee founded in the US. NACA airfoils are identified by a specific four-digit number. In the figure, you can see a number of features of an airfoil, like the positions of the leading edge and the trailing edge, the chord line and its length, the profile thickness and the camber. Some of the dimensions of these features are represented in the NACA number. Note that all dimensions are expressed as percentage or fraction of the chord length. As example, NACA 2412. The first two means that the profile has a camber of 2%, so it has a maximum distance of 2% times the chord length between camber and chord line. The second digit in the number indicates the position of that camber with reference to the leading edge, 0.4 times or 40% of the chord length. The last two digits indicate the thickness of the profile, in this case 12% of the chord length. Let us return to the formula for lift. The other parameters in the formula are the wing surface area and the velocity or airspeed. Both are typical design parameters. During the design of an aircraft, you need to optimize these values with many others in order to obtain the best ratios between performance, weight and costs. The last variable in the equation is the air density, which depends on altitude and temperature. As designer, by choosing a flying altitude, you can have some, although limited, influence on this parameter as well. We have looked at the formula for lift, but how is the lift force generated? One way of explaining is by using the law of Bernoulli. He postulated his formula as the sum of static and dynamic pressure is constant. In formula, P plus half rho V squared is constant. This means that when the speed increases, the local pressure drops or decreases. So in a tube with a throat, the pressure in the narrow section is the lowest, but the airspeed is the highest. This explanation tells that pressure differences can be created by differences in airspeed. These pressure differences can be used to create lift. Note that Bernoulli's law is applicable for particular situations only, for example for low airspeeds and incompressible media. So for an airfoil, the airspeed over the airfoil is usually higher than the airspeed below the airfoil. This is due to the camber of the airfoil and the angle of attack, as can be seen in the first picture. This results in a pressure distribution and can be seen in the second picture. There is some overpressure under the airfoil, but significant underpressure at the upper surface of the airfoil. This pressure distribution results in a lift force and a drag force. With the program NACA Foil Sim, and I recommend you will play with it, you can play with many different parameters of the airfoil and the angle of attack and see what the effect is on the lift force. Can we use Bernoulli's law to measure the airspeed? If we look at the formula, we see that the total pressure is the pressure for zero airspeed. In a Pitot tube, we can make several small holes. One hole is in front of the tube, head-on in the airflow. The air enters the tube from the left-hand side and comes to a standstill. So here we measure the total pressure. Further, we can make several holes at the side of the tube. They measure the local pressure, a pressure in an airflow with velocity V. The difference between the total and static pressure can be used to calculate the velocity as demonstrated by the equation. When we return to the lift coefficient, we said that the coefficient depends on the angle of attack of the wing. This is expressed in a lift curve. For such curve, we plot the value of CL as function of the angle of attack alpha. Most wing profiles have a camber. This means that at a negative alpha or alpha is 0, there is already a lift force available. When increasing the angle of attack, the lift coefficient increases more or less linear with alpha. Look also at the simulations when the flow around the airfoil changes and the lift force increases steadily. Just before its maximum, the curve becomes less linear, and ultimately the maximum coefficient is obtained. A further increase in angle of attack results in a fast decrease of the lift coefficient. This is what we call the stall of the wing. In this case, the lift force drops. And look also again at the airflow around the airfoil, which separates. At landing and takeoff, we fly at low airspeeds. As you can see in the formula, this has a large impact on the lift force. Question is what to do, because the weight of the aircraft does not change. In order to compensate for a lower value of the airspeed, the other parameters should increase. The air density is beyond our control, although most airfields are at low altitudes and therefore the density has rather high values, which helps. The other two parameters, the lift coefficient and the wing surface area, can be changed by using all kinds of high lift devices. In this picture, you see an Airbus A380 with high lift devices. First, I show you the flaps, which are used during landing and takeoff. Second, we can see the slats or leading edge devices, which are mainly used during takeoff. Both devices increase the wing surface area and to some extent they increase the camber of the wing profile and thereby increase the lift coefficient. This is visible in this plot. Slats increase the maximum angle of attack and as a result also the maximum lift coefficient. The flaps at the trailing edge mainly increase the camber of the airfoil and shift the curve upwards. In addition to these effects, both devices also increase the wing surface area. To conclude this lecture, I will briefly mention a number of parameters for the wing geometry. Most of these are optimized during the design of the wing and will have an impact on the lift coefficient and thereby on the lift force. First, there is the wingspan, which is the length from wingtip to wingtip. Then we have the wing surface area. It should be noted that there might be some small differences between several definitions of this area. Next we have the root chord and the tip chord, which represents the chord length at the wing roots and wing tip, respectively. The taper is the ratio between these two. The last parameter to mention is the sweep angle, which is the angle between the leading edge and the y-axis of our coordinate system. This concludes the lecture about the lift force. Next time I will talk about the drag force.